Okay, now we will start chapter 8, vapor power system. What is a vapor power system? We have actually introduced the system in this class already. It is a power plant. So first of all, you have a boiler. You have some fluid, which is usually cold water going in. We call it number 4. And then what is happening inside the boiler is the cold water will gain heat. It gains heat QH and then becomes vapor coming out of it. Liquid goes in, vapor comes out of it. That's 4 to 1 inside the boiler, gaining heat. And then after the boiler, it is a steam turbine. Remember, we always use a diverging duct for a steam turbine because what happens inside is always an expansion process. This is a steam turbine. What a steam turbine does is to generate work. We call it WT. And then cool down steam number 2 coming out of it. And then we need to further cool it down by sending number 2 to a condenser. Further cool it down to number 3. And then before we send number 3 back to number 4, we need to pump up the pressure. And in order for the pump to work, you have to provide electricity or consuming work. The pump has to consume work. We call it WP. Okay, and the next question is, what is the net amount of work you can get out of the cycle? We call it W cycle, which is the amount of electricity you can generate. It's WT, the work you generate, minus the work you consume, WP. So that is the net amount of work you can generate out of this cycle. And next, we're gonna sketch the process on a T versus S diagram. Same as before, we sketch a vapor dome and then two constant pressure lines. Okay, and 4 to 1, same as before. Number 4 will be F point and number 1 will be G point. And then 1 to 2, steam turbine goes straight down. What is the reason? Because 1 to 2 is isentropic, entropy does not change. 2 to 3, go to the left, cool it down. And then 3 to 4, vertical up, goes straight up because it is isentropic again. And the name of this cycle is Carnot. This is Carnot cycle. And today we're going to take one step closer to reality. Okay, there's only one step that is different. T versus S diagram. Again, we have a vapor dome. And then let's sketch two constant pressure lines. Okay, 1 to 2 is the steam turbine and 4 to 1 is the boiler. Usually number 1, what comes out of the boiler is usually not G point, but superheated. So number 1 is usually here. It's usually superheated instead of G point. And that's the only difference. So now 1 to 2, steam turbine still isentropic, you go straight down. You arrive at number 2. And then 2 to 3, you cool it down. Okay, cool it down. Where do we cool it down? We usually cool it down to F point. That's the second difference. So number 3 will actually be F point. And then 3 to 4 is still the pump, so it is still isentropic. You go straight up. And this point is number 4. And then 4 to 1, still the same as before. Okay, and why do we like this one? Oh, first of all, the name of the cycle is called Rankine cycle. Rankine cycle. Why do we usually prefer Rankine cycle over Carnot cycle? Do you recall what is the area of the enclosure? Area of the enclosure tells you one thing. That is W cycle per unit mass. And same thing happens here. The area of the enclosure for Rankine cycle still tells you the same thing. Area of the enclosure is still W cycle per unit mass. So now from the comparison, you can easily tell which one has a bigger area. I've moved number 1 to the right, and I've moved number 3 to the left. So the area of the enclosure for Rankine cycle is actually bigger, meaning the Rankine cycle can give you a higher W cycle. Who doesn't like that? I can get more electricity out of the power plant. Why not? So that's why we prefer Rankine cycle, because it can give us more electricity. Okay, so a few notes regarding Rankine cycle. First one, every step is always reversible. Still, just like Carnot cycle, every single step is reversible. So entropy production sigma is equal to 0. And number 2, constant pressure in 4 to 1 and 2 to 3. That's easy to understand. You can see 4 to 1 is on a constant pressure line. 2 to 3 is on another constant pressure line. So both of them are constant pressure processes. And number 3 is isentropic for process 1 to 2 and 3 to 4, which is the same as Carnot cycle. So that's why 1 to 2 and 3 to 4 are both vertical, because they're isentropic, so entropy, which is the x-coordinate, doesn't change. If the x-coordinate doesn't change, it must be vertical lines. Okay, so again, process 1 to 2 has a name. It's isentropic expansion, same as before. And then process 2 to 3 is the condenser. That's where you lose heat. It's a heat loss process at a constant pressure. And then 3 to 4 is the pump. It's isentropic compression, which is the same as before. And then 3 to 1 is the boiler. That's where you gain heat. So this is a heat gain process at another constant pressure. So now let's talk about each one of them. Let's start from 1 to 2. 1 to 2 is the turbine. What do we want to know about turbine? The purpose of the turbine is to generate work. So naturally we want to know how much work can be generated. What we want to know is W dot turbine over M dot. And how do we look for it? Yes, first law of thermodynamics for a control volume, which is the longer version. Okay, so you just start from first law and your solution is H1 minus H2. It comes from first law. And next one, we move on to the next step. After 1 to 2 is condenser 2 to 3. What do you know about the condenser? What happens in a condenser is you just lose heat, QC, to the environment. So naturally we want to know how much heat will you lose. How do you look for it? First law again. Q dot C over M dot. We can change the subscript to 2 to 3. It's the same thing. And you use first law again. This time the solution is H3 minus H2. It comes from first law. Okay, so one thing that we need to understand here is H3 minus H2. Which one is bigger and which one is smaller? Which one has more energy, number 2 or number 3? Number 2 is the inlet of the condenser, and then you lose heat, you become number 3. So number 2 must have more energy, so H2 must be bigger than H3. However, here, your H3 minus H2, and that will give you a negative solution, which actually makes sense. Like we said, if you lose heat, your solution for heat transfer must be negative. Okay. However, moving on from here, we always prefer to use a positive solution for every heat transfer or work. And we just keep in mind what is the direction of heat transfer or work. So in order for us to have a positive solution, what do? We just simply switch them, H2 minus H3, and that will give us a positive solution. And that is the one we actually use from now on. Okay, H2 minus H3. Okay, so after 2 to 3, we go to 3 to 4, which is the pump. 3 to 4. The pump will consume work, WP, so naturally we want to know how much work will the pump consume. W dot pump over M dot. How do you look for it? Same as before, use first law. Your solution is H4 minus H3. And then last one, the boiler. Boiler is 4 to 1. That's where the water gains heat. And what do you want to know? How much heat does the water gain? So Q dot hot over M dot, or Q dot 4 to 1 over M dot. And from first law, again, your solution is H1 minus H4. So that's every single step. And next, we want to know how much electricity can you get out of the whole cycle. Number 5, we want to know what is W dot cycle over M dot. Like before, W cycle has two components. What are they? Work generated by the turbine minus work consumed by the pump. So this equation becomes W dot T over M dot minus W dot P over M dot, and we have every one of them. W dot T over M dot, what is it? If you forgot, you can go back to our turbine 1 to 2. That's H1 minus H2. H1 minus H2. Minus, what is W dot pump over M dot? Pump is 3 to 4, and it's here. It's H4 minus H3. So from here, you can find how much electricity can be generated. W dot cycle over M dot. And number 6. Number 6. Naturally, we want to know what is the efficiency of the whole power plant. Efficiency is defined as what you get divided by what you pay. What do we get? W cycle is what we get. What do we pay? Q hot. And we divide both of them by time. So we add a dot to each of them. And then we divide both of them by mass flow rate. So do we have the expression for the numerator, W dot cycle over M dot? Yes, we just found it from part 5, and that is H1 minus H2 minus H4 minus H3 divided by Q dot hot over M dot, that's for process 4 to 1. We found it earlier, it's H1 minus H4. And from algebra, the solution is 1 minus H2 minus H3 divided by H1 minus H4. And then there's something new. Number 7, a new parameter is called back work ratio. Back work ratio. We usually use BWR for back work ratio. What is the definition of BWR? It's defined as work consumed divided by work generated. What is the work that is consumed? It's WP, work consumed by the pump. And what is the work that is generated? WT, work generated by the turbine. And then first thing we do is divide both of them by time. So add a dot to each of them. And next thing we do is to divide both of them by mass flow rate. Do we have an expression for the numerator? Yes. W dot P over M dot, that's H4 minus H3. And W dot T over M dot, that's 1 to 2. 1 to 2. Do we have it? Yes, it's H1 minus H2. So now, do you want to have a big BWR or a small BWR? You want work consumed to be small, and you want to work generated to be big. So you want BWR to be as small as possible. BWR, the smaller the better. The smaller BWR you have, the better your design is. So now if you take a look from part 1 to part 7, what do you notice? Everything is just a function of h. So for example, for BWR, you just need to find h1, h2, h3, h4. And for part 6, efficiency, the same thing. You just need to find h1, h2, h3, h4. And for W dot cycle over M dot, you still need to find 4 enthalpies. So now you realize if you ever want to solve the question for a Rankine cycle, all you need to do is to look for H1, H2, H3, and H4. As soon as you find enthalpy of every single point, the rest will just be very easy.